Title Unraveling Them Event Horizon. What if I told you that there are regions in the universe where time ceases to exist and light cannot escape? What lies beyond the event horizon of a black hole? And how does it challenge our understanding of reality? Today we dive deep into the enigma of black holes, where physics bends and our imagination is pushed to its limits. The central theme here is the profound mystery surrounding black holes and what they reveal about the fabric of our universe. These cosmic giants not only provoke our curiosity, but also force us to confront fundamental questions about existence, time, and space. Imagine standing on the edge of a vast abyss, knowing that if you take a step too far, you'll be engulfed by an unseen force. That's precisely what happens at the event horizon of a black hole. But what does it mean to cross that threshold? And why do black holes captivate scientists and dreamers alike? Let's start with the basics. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. This process creates an incredibly dense region in space, with a gravitational pull so strong that even light cannot escape. As physicist Stephen Hawking famously said, "Black holes are not the end, they are just the beginning." But what exactly lies beyond this cosmic boundary? First, we need to understand the event horizon itself. Picture a point of no return. Once an object crosses this boundary, it cannot escape. It's a one-way ticket into mystery. The event horizon marks the limits of our knowledge. Beyond it lies a realm governed by laws that challenge our current understanding of physics. Why does this matter? Because it raises questions about causality and the nature of reality. If we can't observe anything beyond the event horizon, how can we know what happens there? This uncertainty fuels scientific inquiry and philosophical debate alike. Now, let's explore what happens if you were to fall into a black hole. Imagine you're an astronaut approaching a stellar giant. As you get closer, the gravitational pull becomes stronger, distorting space and time around you. The phenomenon is known as spaghettification, where the immense tidal forces stretch your body into a long, thin shape like spaghetti. Yes, it sounds outlandish, but it's a real consequence of extreme gravity. Renowned astrophysicist Neil deGrasse Tyson puts it succinctly: "The universe is under no obligation to make sense to you." And indeed, as we venture into the realm of black holes, we find ourselves grappling with concepts that defy common sense. But what lies at the core of a black hole? The singularity, an infinitely dense point where all known laws of physics break down. It's a place where time and space lose their meaning. As you approach this singularity, time itself stretches and warps. From your perspective, time would slow down relative to observers far away. But for those outside, it appears you'd never quite cross the event horizon. You'd slowly fade from view instead. Why should we care about this paradox? Because it challenges our very understanding of time and reality. Are we merely prisoners of time, or is there more to our existence than we perceive? As we unravel these mysteries, we inch closer to answering questions that have plagued philosophers and scientists for centuries. Let's consider another intriguing aspect: Hawking radiation. Stephen Hawking proposed that black holes can emit radiation due to quantum effects near the event horizon. This means that black holes aren't entirely black. They can slowly lose mass and energy over time. In essence, they could eventually evaporate. What does this imply? It suggests that even the most formidable structures in the universe are not permanent. Everything has a life cycle, even black holes. This idea resonates with our understanding of life itself. Nothing lasts forever, and change is inherent in the cosmos. Now, let's address an essential question. Can we observe black holes directly? The answer lies in their effects on nearby matter. When a black hole pulls in material from its surroundings, it forms an accretion disk, a swirling mass of gas, and dust heated to extreme temperatures. This disk emits powerful X-rays that we can detect with advanced telescopes. In 2019, humanity achieved a historic milestone by capturing the first ever image of a black hole's shadow at the center of the galaxy M87. This image provided tangible evidence of their existence and opened new avenues for research. What does this breakthrough teach us? It reminds us that even in darkness, there's light to be found. Knowledge can emerge from the most mysterious places. But let's not forget about supermassive black holes. These giants lurk at the centers of galaxies, including our Milky Way. They can be millions or even billions of times more massive than our Sun. Their gravitational influence shapes the structure and dynamics of entire galaxies. Why is this significant? Understanding supermassive black holes helps us unravel the history of galaxies themselves. They hold clues to how galaxies form and evolve over cosmic time scales. Now, imagine a hypothetical scenario where you could travel through a wormhole, a theoretical passage through space-time that connects distant points in the universe. Some scientists speculate that black holes might be gateways to these wormholes. Could they lead us to other dimensions or even other universes? Theoretical physicist Kip Thorne once said, "The only thing that can travel faster than light is information. If wormholes exist within black holes, they could facilitate communication across vast distances almost instantaneously." This idea may sound like science fiction, but it ignites our imagination about future possibilities. As we dive deeper into these theories, we must confront another fundamental question. What happens when we attempt to merge general relativity with quantum mechanics? Black holes serve as the ultimate testing ground for this endeavor. They challenge our understanding of gravity at extreme scales and offer insights into unifying these two pillars of modern physics. What does this mean for us? It means that black holes are not, if you're enjoying this, consider liking the video and subscribing for more insights. Just celestial objects, they are gateways to unlocking the secrets of the universe. They compel us to rethink our notions of reality and explore the unknown. As we approach the conclusion of our exploration, let's reflect on how black holes shape our understanding of existence itself. They remind us that there are limits to our knowledge, but also endless possibilities for discovery. Black holes symbolize the mysteries waiting to be unraveled, a testament to humanity's insatiable curiosity. So, what lies beyond the event horizon? We may never fully comprehend its secrets, but in our quest for knowledge, we find purpose and inspiration. Black holes challenge us to embrace uncertainty and seek answers in the closing. Remember this: the universe is vast and full of wonders yet to be discovered. The next time you gaze at the night sky or ponder the nature of existence, consider the black holes lurking in its depths. Enigmatic giants that remind us of how much there is still left to learn. As physicist Carl Sagan beautifully stated, somewhere, something incredible is waiting to be known. Let that thought guide your curiosity and fuel your desire to explore. The cosmos has so much more in store for us. What if I told you that black holes might hold the key to understanding not just the cosmos, but the very fabric of reality itself? What awaits beyond the event horizon, and how does this challenge everything we think we know? Today, we embark on a journey into the heart of darkness, exploring the tantalizing mysteries of black holes and the profound questions they raise about existence, time, and space. Our central theme revolves around the enigma of black holes and what they reveal about our universe. These cosmic phenomena not only spark our curiosity, but also compel us to confront fundamental questions about life, death, and the nature of reality. Let's begin by clarifying what a black hole is. Imagine a massive star, one that has burned through its nuclear fuel. In its final moments, it collapses under its own gravity, creating a region in space where the gravitational pull is so strong that not even light can escape. As physicist Albert Einstein once said, "The most beautiful thing we can experience is the mysterious." And indeed, black holes are shrouded in mystery. The event horizon marks a critical boundary, the point of no return. Once crossed, there's no escape. But why does this matter? It challenges our understanding of causality. If we cannot observe what lies beyond this boundary, how do we even begin to comprehend it? This uncertainty fuels both scientific inquiry and philosophical debate. Now, let's take a closer look at what happens as you approach a black hole. Imagine you're an astronaut nearing this cosmic giant. As you get closer, the gravitational pull becomes increasingly intense. Space and time warp around you, a phenomenon known as spaghettification. Yes, it sounds bizarre, but under extreme gravity, your body would stretch into a long, thin shape. Neil deGrasse Tyson aptly states, "When you're in a black hole, you don't know you're in a black hole until you're dead." But what happens at the core of a black hole? This brings us to the singularity, a point where density becomes infinite, and our current understanding of physics. As you near this singularity, time behaves strangely. It stretches and warps. To you, time would seem to slow down relative to observers far away. However, from their perspective, it appears you never quite cross the event horizon. You slowly fade from view instead. Why is this paradox significant? It forces us to rethink our relationship with time. Are we bound by its flow, or could there be more to our existence? These questions propel us forward in our quest for understanding. Let's turn our attention to Hawking radiation. Stephen Hawking proposed that black holes can emit radiation due to quantum effects near their event horizons. This means black holes aren't entirely black. They can lose mass and energy over time. Imagine that even the most formidable structures in the universe are not permanent entities. This notion resonates with the broader theme of impermanence in life. Everything eventually changes. Now, can we observe black holes directly? The answer lies in their impact on surrounding matter. When a black hole consumes material from its environment, it forms an accretion disk, a swirling mass of gas and dust heated to extreme temperatures. This disk emits powerful X-rays detectable by advanced telescopes. In 2019, humanity achieved a groundbreaking milestone by capturing the first image of a black hole's shadow at the center of the galaxy M87. This image provided tangible evidence of black holes' existence and opened new avenues for research. What does this discovery teach us? It illustrates that even in darkness, knowledge can emerge. Light can be found in the most mysterious places. Let's not overlook supermassive black holes. These giants reside at the centers of galaxies, including our Milky Way. They can be millions or billions of times more massive than our Sun. Their gravitational influence shapes entire galaxies, structures and dynamics. Why should we care about supermassive black holes? Understanding them helps us unravel the history of galaxies themselves. We gain insights into how galaxies form and evolve over cosmic timescales. Now, picture a hypothetical scenario where you could travel through a wormhole, a theoretical passage through spacetime connecting distant points in the universe. Some scientists speculate that black holes could serve as gateways to these wormholes. Could they lead us to other dimensions or even parallel universes? Theoretical physicist Kip Thorne once said, "The only thing that can travel faster than light is information." If wormholes exist within black holes, they could allow for instantaneous communication across vast distances. This idea may sound like science fiction, but it ignites our imagination about future possibilities. As we delve deeper into these theories, we must confront another fundamental question. How do we merge general relativity with quantum mechanics? Black holes serve as the ultimate testing ground for this endeavor. They challenge our understanding of gravity at extreme scales and offer insight